Okay, so welcome everyone to today's seminar on automorphic forms. It's a pleasure to have Ziqi Guo from Beijing University, and he will talk about modular heights of unitary Shimura varieties. So Ziqi, please.
Okay, so hello everyone. It's my pleasure to give a talk here about our recent work about the modular heights of unitary Shimura varieties. Okay, so today's talk will divide mainly into three parts, I think. The first part will introduce the main theorem about our work. I think there are two main theorems. The first main theorem is about the formula of modular height, and the second main theorem is about the height of the same point on the unitary variety. And for the second part, we would like to introduce some background and motivation about this so-called special value formula and talk about some history. And third part, if we have time, I would like to explain some of our idea of the proof. So this will be the three parts of today's talk. So let's begin the first part about the main theorem. Here's a brief introduction. In our work, we'll fix the same extension E over F of here F is a totally real field. And we also need to fix a Hermitian space over E, which has signature N1 at exactly one Archimedean place, and N plus 1, 0 at all the other Archimedean places. And with this information, we can define the Shimura variety associated to the unitary group of the Hermitian space. Here U is the unitary group, not GU, not the unitary group with similitude. And after choosing a suitable compact subgroup of this G, we can define a Shimura variety of dimension n over the reflex field E, and we'll explain how to define this compact subgroup. And there will be a good line bundle L on X equipped with a natural Hermitian metric. And then we can define a canonical integral model, mathematical X over OE. And we can also extend the line bundle L to the arithmetical one on the integral model. And the goal of our work is to compute this ratio, just the top arithmetic self-intersection number, and over the geometric self-intersection number, means intersection number on the genetic fiber. And we call this one the modular height. And this is our goal. Okay, so we begin with some basic definition. Here we give a definition of the unitary Shimura variety. Simply speaking, there is a Hermitian symmetric domain for G. This D is a Hermitian symmetric domain which consists of all the negative lines in the projective space. Here the iota is a fixed Archimedean place such that the Hermitian space has signature N1. So there will be some negative lines, and these negative lines form a Hermitian symmetric domain. And it is connected and carries the natural the U invariant complex structure. Now then, for any open compact subgroup U of GQ, so don't be confused with these two U. We'll have a Shimura variety with 3 points, just look like this one. And in fact, this Shimura variety is smooth over the reflex field E and has dimension n. So this is the definition of our Shimura variety. And now we would like to talk about the special Hermitian lattice we need to choose. So for here, a small v is a finite place of the total real field F, and this var pi is a uniformizing parameter of the local field EV, and we denote by this lambda wedge the dual lattice with respect to the Hermitian pairing. Here we should emphasize that this dual, we do not take the trace over trace of E over F. We simply take the Hermitian pairing. So do not confuse here. And we will introduce the following definition about the lattice. We call such lattice self-dual if the dual of such local lattice is just itself, the dual under Hermitian pairing. And we call it pi modular if the dual is if just pi -1 times the lattice itself. And we also call it almost self-dual, almost pi modular, if this inclusion has colis 1. So actually, we should say that when the later two definition depends on the rank of the Hermitian lattice. When the rank of the Hermitian lattice is even, there exists this pi modular lattice. But when the lattice has rank odd, there won't exist such pi modular lattice, but only exists the almost pi modular lattice. And then with all this local definition, we fix a special Hermitian lattice at all the finite fields or finite places, such as the lambda v is self-dual at all the places unramified in E over F. And we fix that when v is ramified in E over F, we choose this lambda v to be pi modular or almost pi modular, depends on the parity of n, as we talk about when n is even or odd, the existence of such pi modular or almost pi modular lattice it depends on the parity of n. Okay, now we'll go to the integral model. So we'll choose U to be an open compact subgroup of G, such as for any finite place V, UV is a stabilizer of the Hermitian lattice we choose before. So actually we mean this U need to be somehow maximum because it is a stabilizer of the Hermitian lattice we choose in the last page. And we have the following theorem about the integral model. I think this theorem is first proved by Rappaport, Smitherling, and Zhang. Actually, I should talk about this theorem first. So we need to put certain restriction on the same extension U over F. For example, for the prime 2, we do not want 2 is ramified in U over F or somehow some other condition. With some condition on U over F, then there will be a regular integral model, Mescal X, over this spec OE. And in our case, we mean by our choice of the Hermitian lattice lambda, this integral model is actually smooth. And when F, the totally real field, is not Q, this is proper. So this theorem was first proved by Rappaport, Smitherling, and Zhang for the so-called RSZ Shimura variety. And then later in 2023, Lin and I think in his paper with also appendix of Xu Yijie, they construct this global integral model from the RCA integral model to this unitary case. So actually, in our case, we'll have a very good integral model. It is smooth. It is smooth at every finite places. So it is very good. Now we would like to talk about the Hodge bundle. So first, we define this line bundle on the generic fiber. Actually, this is just the descent of the tautological bundle on the Hermitian symmetric domain. As we define, D just contains those negative lines. So you can define the so-called tautological bundle on D. And it carries a natural Hermitian metric, which defined as this one. Here, this left angle, right angle means Hermitian norm. This is a Hermitian norm because the D contains all the negative lines. So this Hermitian norm is always negative, and you take the negative one, so you get a positive one. And this is a Hermitian metric, which is also equivariant under the action of the unitary group. And then we can define the LU on the Shimura variety, which is the descent of this tautological bundle. And then this line bundle can extend canonically to an arithmetic one on the integral model, which is also ample. And here we should emphasize that the unitary Shimura variety is only of abelian type. It is not of PO type, so there's no modular interpretation of the unitary Shimura variety. But if you pass to the RSA Shimura variety, RSA unitary Shimura variety, which is of PL type, then you can get some modular interpretation of this arithmetic hot bundle on the RSA Shimura variety. And then we denote by this one, just normalized as a generic fiber to be the degree 1 arithmetic one cycle on the integral model. So by our definition, the modular height of the Shimura variety is just this one. It's just the arithmetic degree and over the degree on the generic fiber. So this is what we need, what we want. And now we would like to state the main theorem of our work. So the main formula is here. Here, eta is the quadratic character associated to U over F via the class field theory. And this LF is the incomplete half F function, means there's no Archimedean part, just the finite part. And when F is not Q, because when F is Q, I think there will be some, you need to take some compactification, and we do not work on that. So we have such formula. So you can see the main term is the first summation is just the log derivative of the special value of this L function. And this term, just the log derivative of L function when S is 1, actually this comes from the height of same point, I think. And for the second line, these mainly come from the Archimedean part. That means the metric of the line bundle. So we will get this small gamma, the Euler constant, and something like that. And for the third line, this is because here df is a discriminant of f over q, and d e over f is the norm of the relative discriminant of e over f. This comes from I think the ramification of f and also e. So this is our main formula about the modular height. And we would like to introduce some related works. I think the modular height of special Shimura variety has a long history. First by Bose and Kuhn in 2001. They proved the explicit formula of the modular height of modular curve x1, and the formula is very short, very clear. And then in 2006, Kudla and Rappaport and Yang, they proved the modular height of quaternion Shimura curve when f is q. And later in 2023, Professor Yuan proved the formula when f is totally real. And also for higher dimensional case, Bernier, Burgess, Gill, and Kuhn in 2007, they proved a formula of modular height of Hilbert modular surface, also when f is q. And for the orthogonal case, Holman proved the formula when f is q up to some back prime, up to some log p, because the orthogonal case you can imagine when for the prime 2, it's very difficult to compute a very clear formula, very explicit formula. It's very difficult. So Holman do this formula in 2014. And finally, for the Shimura variety of unitary similitudes, GU, Brunier and Howard prove the formula when f is q. And we should emphasize that they use a different arithmetic line bundle and also a different level group. As we explained before, the Hermitian lattice we choose in the Hermitian space is a little bit different with their Hermitian lattice they choose. And also, I think they need to do some compactification of the integral model because they consider a case of f when f is q. So these are some related works. And now we would like to introduce a fixed saving point, a very special saving point on the unitary Shimura variety. So let's fix an orthogonal decomposition. Here V is the Hermitian space we choose before, and W is the Hermitian subspace of dimension 1 with signature 0, 1 at exactly one occupant place, just like V. And at all the other occupant place, it has signature 1, 0. And we also require the Hermitian determinants, which means you can write the Hermitian forms in a diagonal metric, and you can compute the Hermitian determinants easily. We require the Hermitian determinants of V and W are the same. And you can imagine that this W will define a zero-dimensional Shimura variety given by this W. Here actually I use this mass PBW because you can base change this W to the RDL, and there's a so-called and the concept so-called incoherent or coherent space. For example, a Hermitian space over the RDL is called incoherent. If it is not the base, if it cannot be written as a base chain from a Hermitian space over E. Okay, so actually, I mean, for this decomposition W, we can define a so-called zero-dimensional Shimura variety, and this will give a same point on the Shimura variety, and we can normalize it to have degree 1 on the generic fiber. So this will be the same point. And we can also consider its Zariski closure on the integral model. This will define a one cycle on this integral model, which also has degree 1 on the generic fiber. So this is the same point we need to consider. And also under the complex uniformization, this same point is represented by we can write down explicitly write down this. Here E is represented by a negative line, where E is the generator of this one-dimensional Hermitian space W. So we also proved the following theorem about the height of this same point on the integral model of the unitary Shimura variety. So the formula is written as this. Here again, eta is a quadratic character associated to E over F via the classical theory. And LF is again the incomplete Heckel function. And here is the explicit formula about the height. Here, the height of the same point means we just take the arithmetic intersection between this arithmetic Cauchy bundle and this P, this arithmetic same cycle. And this is also the formula used in our work. Actually, this theorem is proved from the height of same point on the quaternion Shimura curve, because there are some relation between the quaternion Shimura curve and the unitary Shimura curve. You can imagine there's a series of morphisms, so you can just carry the work, the height on quaternion Shimura curve to the case of unitary Shimura curve. And also there are many related results. I think also by Kula, Rappel, Yang, they prove a height of same points when F is Q in 2006, and also by Yuan and Zhang in 2015 when F is general, totally real field. They proved the average Combs conjecture using the height formula of same point on the quaternion Shimura curve. This is the main part of their proof. Besides, the same point of orthogonal Shimura variety, Andreatta, Groen, Howard, Malapuzzi, and Pera, they proved the height of same point on the orthogonal Shimura variety, the G-spring one, when F is Q. And they also used this formula, the height of same point, to prove the average Combs conjecture in a different way. So these are some related works. Okay, so this is our first part. And let's move to the second part. I'd like to introduce some motivation and background about this research. So I think the story we can begin from the well-known Gross-Zagier formula. Roughly speaking, so Gross-Zagier formula proves something on the modular curve. So in their setting, let n be a positive integer and f is a new form. And for the imaginary quadratic field k and a character chi, and their L series is this Rankin-Selberg L series. And they need to assume so-called Hickner condition on K, such that K has such as every prime factor of n is split. And then they will find that the L series, the functional equation of L series has the signature -1. So the special value of the L series is 0. And then they need to consider the derivative of this L series. And with this setup, they also consider this P. This P, you can imagine this P is just a special point on the modular curve and defined by the modular interpretation. Here x0n is the modular curve of Q, and for every non-zero ideal I, and using the modular interpretation, this n would give a point pi, and here we need to use a hidden condition such as n is split at each prime. And then we'll get a point on the Jacobian. The well-known Gross-Zagier formula in 1986, they actually prove the Unitary height of this special point on the Jacobian variety. They connect the height with a special derivative of L function. So I think this might be the beginning of the special value formula. And inspired by this work, also in 2012, Yuan Zhang, they proved a generalized Gross-Zagier formula over the quaternion Shimura curve, inspired by their work. And there's a big picture called the Kudla program we need to emphasize as in 1997, Kudla started this program. Its main concern the relation between the specialty cycles and also the arithmetic version, and their relation between the values or the derivatives of Eisenstein series and L function. So I think Kudla began his program on the orthogonal Shimura variety, and in the later few years, there are many results on the orthogonal and unitary case. So I think the core object of the Kudla program is a generating series formed by the special cycles, and also as well as the arithmetic version. Means you can extend all these special cycles to the integral model. So roughly speaking, the generating series is an analog of the classical Sela series in both geometric and arithmetic sense. Here, the geometric we mean just on the genetic fiber, and the arithmetic we mean on the integral model. So there would be some connection between this generating series and the Eisenstein series. So we would like to explain this idea. So we begin with a very elementary example from Lichau's note. It's an example from the sum of two squares. So there's a very classical problem that in how many different ways we can represent n as a sum of two squares. A theorem by Jacobi in 1829 is that okay, the different ways Rn can be represent the number of representation can be written down explicitly by the factors of n, this formula. So Jacobi proved this formula using the classical modular form and also some J function prove this formula using his Jacobi Sela series. So in a modern way, we can just write this one. We can write this theta to be this function where the coefficient of each qn is just a number of representation of n into two squares, and you can write down this Jacobi theta series, and you can check that this theta series is actually a classical modular form, which is half weight, and then you can take the square of this theta. You can get a weight 1 modular form. Then, but you also know that when the weight is 1 and the level group is gamma 1 4, then this space is generated is one-dimensional and is generated by Eisenstein series. So you can simply check the constant coefficient, can match this coefficient 1 with this theta square, and then you can get the coefficient of this non-constant term, means this Rn. You can match this Rn with this one, so we can conclude this theorem. So I think with this idea, we can summarize there's a deep relation between the theta series and the Eisenstein series. And before we go further, we need to define the so-called weighted representation. The classical weighted representation here, in our case, we need to use a weighted representation of U11, and B is a Hermitian space we fixed before, and we consider the reductive dual pair GH, which is U11 and UV. And for phi is a Schwartz function. There's a weighted representation right down by this one. So this is the weighted representation in our case we need to use. Okay, so with this weighted representation, we can define the theta series and Eisenstein series in our case. So this theta series is very simple. This theta GH with a fixed choice of Schwartz function phi is simply defined using the weighted representation. Take the summation of all these x in the Hermitian space. And we can also define the Siegel Eisenstein series. Here gamma is taken over all these quotients. And this is a classical Ziqi Eisenstein series of the case U11, and it also has a Automorphic continuation to the complex plane. And the classical Ziqi Wheeler formula in Unitary case here is proved by Ishino in 2004. So there exists a constant chi such that the integral of the theta function, the theta series, is equal to the special value of the Eisenstein series. So this is the classical Ziqi Wheeler formula, and the classical Ziqi Wheeler formula prove identity like the integral of zeta series is the special value of Ziqi Eisenstein series. And you can also talk about the local Ziqi Wheeler formula. I mean, you can talk about the Fourier expansion of the Eisenstein series, and then this coefficient of this expansion will be the Whittaker function, and you can talk about the local Whittaker function is defined by this integral, and using a standard series, so the Eisenstein series, the Fourier expansion, it can written as the summation of this Whittaker function indexed by this A in F. So you can also talk about the local Ziqi Wheeler formula, just a counterpart of the global one. It's also the integral of the theta series locally. It becomes the special value of the local Whittaker function. You can also talk about this local formula. And now we would like to move to the geometric one. So here, this is a very interesting example about the Hurwitz class number formula. I think this will help to understand the idea of the generating series. So for any positive integer d, we can define the so-called Hurwitz class number HD, which is the weighted size of this SL2Z equivalent class of its positive definite binary quadratic form. Just means these quadratic forms has discriminants negative d, and you count the weighted size. Here we need to add the multiplicity because there will be some extra automorphism when these two special case. So come with multiplicity. So the Hurwitz number also appears as a Fourier coefficient of the Ziqi series on SP4. And there's a deep theorem proved by Kronecker in 1860, Gilster in 1883, and Hurwitz in 1885. So on the one hand side, when M is not a perfect square, the left-hand side is an elementary summation. And on the right-hand side, it is the summation of some special value of the Hurwitz number. So this formula is very interesting. I think they prove this formula also using the classical modular form. But nowadays, there's a very good geometric interpretation of this formula. I also cited this example from Lichau's note. So the geometric proof is very simple. You can simply consider the modular curve y, just the quotient of SL2D of the upper half plane, and take x to be the y times y. It is the modular surface. And you can define the divisor Zm over x using the modular interpretation of the modular curve. Just Zm just contains all these points e prime with isogeny phi, such as the phi is isogeny between e and e prime with degree n. So it will give a divisor on x. So on the one hand, you can compute using some numerical equivalence or cohomological equivalence of Z1, because you can imagine Z1 is just a diagonal embedding, because you can follow the definition. Z1 is just y diagonally embedded into the surface x. So because the compactification of the classical modular curve y is P1, so the compactification of x is P1 times P1. And some exercise from Hodgson, I think, the diagonal Z1, you can use the numerical equivalence to compute it. You can get this left-hand side. And on the other hand, you can use the modular interpretation of Zm and Z1. The intersection Zm of Z1 is simply parametrized by this point. Here, we should emphasize that the condition that M is not a perfect square ensures that this intersection is proper. When M is not a perfect square, this intersection is proper. So you can talk about this intersection. And then some theory about complex multiplication will tell you that the number of such points is equal to the summation of the Hurwitz number. So this will be a very short and very beautiful proof. So I think this is the idea of the Unitary series. So to summarize, there is a deep relation between the intersection number of special divisors and Fourier coefficient of the Ziqi series. So I mean, you can if in this example we only choose one m, but if you let m varies, for example, you can take m to be all the positive integers, you can get a series in some sense, and this will be the idea of the general series. So the general series is just a geometric analog of the zeta series, first proposed by Kula, and also called the geometric zeta series in literature. So its coefficient, just like we said, just like the previous example, Zm, the coefficients are some special cycles on the Shimura varieties, and it is also in some case you can prove this series is modular or automorphic in some sense. Means you can just apply a linear functional with some convergence condition, I think, and you can apply the linear functional on the trill group to get a real one, to get a real modular form. So I think many mathematicians study this modularity of general series in many different cases by many mathematicians. So I would like to introduce the special divisors in our case. So on the unitary Shimura variety, for any x, in the Hermitian space, also after a quotient of the level group U. If X generates if the one-dimensional subspace W0 generated by X is a positive definite subspace of dimension one, then you can also define the Kulla special divisor. Here you can just understand that the orthogonal complement of X, this W0 perp, satisfies the it just looks like V, but with only codimension one. So you can define a codimension one unitary Shimura variety, and this codimension one unitary Shimura variety will be the Kulla special divisor. And also for convenience, when the one-dimensional subspace X, the W0 generated by X is not positive definite, we then define this special divisor to be zero. So this is the definition of the special divisors on unitary Shimura variety in our case. So it's just simply the codimension one Shimura variety. And then we can form a general series of special divisor case. So we should emphasize that in general, you can also define a general series of special cycles in hierarchical dimension. But here, in our work, we only need to use the general series of special divisors. So for any Schwartz function invariant under the level group, and for any t, here f plus means it is positive at all the Archimedean place. You can define the weighted special divisor to be the sum of this simple special divisor. Here again, this left angle, right angle means a Hermitian norm. And you can define the Kulla's generating functions of divisors in the Chou group with complex coefficient as follows. Here, the constant term is just the dual of the Hodge bundle L, and also phi zero as a. And the non-constant term are mainly consist of ZT, just the weighted special divisor. Here QT, here Q is here Q is explained as the follow. Tau is a point on d times the upper half plane, and you can imagine this QT is just the Archimedean part of the general series, and this ZT forms the finite part of this general series. And note that this general series, you can also write this general series into a variable of G. For example, you can just fix a special tau in this HD, fix one tau, and you can apply the action of G on tau. So you can write this general function as a variable, as a function in the variable G, and also a variable phi, because the weighted special divisor depends on the Schwartz function phi. So there will be a so-called geometric Ziqi weighted formula. Just look like this one. It means that if you define the degree of the generating function, means the generating function, it just take value in the divisor class, and you intersect this divisor class with exponential of L of the Chern class of L, and you'll get the geometric Ziqi weighted formula. It was proved by Kulla first in 1997 in the case of orthogonal case, and the similar result will hold for the unitary case. It will say that the degree of the general series of divisor will be the degree of the Shimura variety X and times special value of the Eisenstein series. So to summarize, there will be a precise identity between the generating series and the special value of the Ziqi Eisenstein series. So this is the story on the generic fiber. So now let's move to the arithmetic case. So we can ask a similar question on the integral model. For example, x and y. So y is the modular curve, just we defined before, and x is y times y, the modular surface. You can consider its canonical integral model, and you can also extend the special divisor Dm in the example to an arithmetic divisor on the integral model. So a good question is to ask if there will be a formula of this intersection of this arithmetic divisor on x, and can you match this intersection with some special value of Eisenstein series or something like that? So the answer is yes. So let's define E tau s to be the Ziqi Eisenstein series of SP6 of which 2. And then you can note that the special value will be 0. And there's a formula by Gross-Keating in 1993. And also Gross, Kudla, Zagier, they proved the similar formula in 1997. The formula is that you take the arithmetic intersection of this arithmetic special divisor on the integral model, and you will get the special derivative of the Eisenstein series, some summation, so like that. So this is very interesting. So you pass to from the geometry case to the arithmetic case, the right-hand side just pass from the special value to the special derivative. So to summarize, there will be a deep relation between the arithmetic intersection number of arithmetic special divisor and the derivative of the Fourier coefficient of the Ziqi series. So you can ask at least 2 questions, just like the geometric case. Does there exist an arithmetic general series such that the coefficients are arithmetic special cycles on the Shimura varieties? So, I mean, can we extend the general series to the arithmetic case? And you can also ask, does there exist a Ziqi formula like the geometry case? Can we extend it to the arithmetic case? So we want to match the special arithmetic intersection between and the special derivatives. So in general, the question remains open, but I think there will be lots of progress. For example, for the first problem, it's called the Kudla's modularity problem. We will here again we will only talk about the divisor case. So the question can be stated as this. So can we find an arithmetic divisors, this mathematical dx, on the integral model, extending the special divisors explicitly and canonically, such that this arithmetic generating series is modular? Here, we call this arithmetic generating series modular if we can apply any linear functional on the arithmetic divisor class, and then you can get a real modular form. So there are some known cases. For example, Kudla-Repel-Yang, they proved the case of quaternion Shimura curve of Q in 2006, and also Brunier-Berger-Skill, Cohen, they proved the case of Hilbert surface over Q in 2007. Howard, Malpuzzi-Pera, they proved this case of more also orthogonal Shimura varieties over Q in 2020. And Brunier, Howard, Kudla-Repel-Yang, they proved this arithmetic modularity problem with a certain level structure of the unitary case also in 2020. And there's another idea by Shou Zhang in 2020. It's called the admissible arithmetic extension. So roughly speaking, so if you fix an arithmetic line bundle L on the integral model, then for the ZT, the special weighted divisor on the generic fiber, there will be a unique so-called L admissible extension of this special divisor on the integral model. And here I should remark that when the integral model this mathematical X is smooth, then this L admissible extension is very easy to compute. You can just take the Zariski closure of ZT and then you can get the L admissible extension. But when X has some is only regular, not smooth as some bad prime, you will take more effort to compute this L admissible extension. There will be some extra vertical dividers in defining the L admissible extension. So inspired by this idea, uh, um, the proof and Qiu Songling proved the modularity, proved the arithmetic modular arithmetic general series of dividers over the unitary varieties, and his situation is consistent with ours in 2023. So using the language of this admissible extension. So here is the key idea. The key idea is very simple. It's a so-called almost modularity property. So you can imagine you have a modular generating series on the generic fiber, and you can simply take the Zariski closure on the integral model if the integral model is smooth, and you can and this arithmetic generating series may not be modular in the arithmetic sense, but if you intersect this arithmetic general series with any arithmetic one cycle, such that the degree of this arithmetic one cycle is 0, and then this intersection number, this is actually this is a series because you can vary tau. This is a series. Then this intersection is a number, and this is modular. So this is the key idea. And in our proof, we also use the idea. So using this, you can help to construct an arithmetic generating series of dividers. So here is also a formula in our work. I think we can call this arithmetic Ziqi formula for dividers in our case. So I would like to explain the notation here. Here, this mathematical ZT is just the arithmetic special weighted divider. And the left-hand side, you just intersect this special divider and take a summation with the exponential of the Hodge-Bundle ln. And you need to normalize on the generic fiber. You need to normalize on the generic fiber. And on the right-hand side, you can see that here the first term is here, this E star, it means the non-constant term of the Eisenstein series, because here on the left-hand side, we do not have the constant term. So here we only consider the non-constant term. So here Y0, you can imagine in the Hermitian space, you can choose a very good Y0, good vector Y0 in the Hermitian space. So then you can define the special divisor zy0, which is very good as a codimension one Shimura variety, and you can talk about this codimension one Shimura variety's modular height. Since you can choose y0 very special, you can use induction to compute this the first term on the right hand side, and the coefficient is just like the geometric Ziqi formula. It's just the special value of the Eisenstein series. And there will be many error terms come from dy. You can imagine for general T, for example, T may contain many bad primes. And then the special divisor ZT will be different from this zy0 if you choose zy. For example, you can choose the Hermitian norm of y0 is 1. When T is very ramified or contains some ramified prime, then there will be some difference between the modular height of ZT and the dy0. So this dy just measures this difference. So this dy is associated to each vector y. As I explained, y is different from y0. So there will be some extra term. And you can finally, in our explicit computation, you can match this explicit different dy to the derivative of Eisenstein series, and all the terms can be computed explicitly. So actually, this dy is a special value of Eisenstein series plus the special derivative of Eisenstein series. So if you take a summation of these two terms on the right-hand side, the right-hand side will be simply the derivative of some of Eisenstein series. So I think this will call, I would like to call this the arithmetic Ziqi formula. So as I explained, this dy has a very explicit formula, but it is very long, so I did not write down on this PPT. So in general, the story of arithmetic formula is a very big project. So there are many local results, both on the Archimedean place and also the non-Archimedean place. So locally, at infinity means the green function part. Li Feng proved the unitary case in 2011, and Brunner Yang proved the green function part in 2020, and also Garcia and Sankaran proved both case in a more general setting using some other technique in a more general setting in 2019. And there are some few example in the known example in the global case. For example, I think Li Shan Zhang Wei, they proved identity between the arithmetic degree of Kudla ripple cycles of full rank. Here full rank means you can just consider here full rank means one cycle. You can define the special divisor. You can just intersect them to get a one cycle. So the full rank means one cycle, and they match this one cycle arithmetic degree of this one cycle to the derivative of some incoherent Eisenstein series in 2019. And then Ryan Chen extend this identity to co-rank one. Means you can consider, I think, two cycles and then intersect the two cycle with an arithmetic line hot bundle. I think and these are some known results. So let's move to part 3. I would like to briefly introduce some of the idea of our proof. So actually, in one word, we try to match the arithmetic intersection number of the arithmetic general series and also with the special value and also the derivative of L function, and then compute the modular height by induction. As I already explained in the arithmetic Ziqi formula I posted before, you can imagine you can choose a good vector y0, and then the special divisor given by y0 will be a good one to use induction. So roughly speaking, we'll consider the following arithmetic intersection. Here, this mathematical Z is just the arithmetic, is just the taking the Zariski closure of the geometric generating series on the integral model. You just take the Zariski closure because our Shimura variety is smooth, and you intersect it with this normalized one cycle, it has degree 1 as a generic fiber, and then the constant term, you can see the constant term, because the constant term of this general series is just the dual of the hot bundle. So the constant term will be the modular height we need. And while the non-constant term, you can imagine, it's just intersection between each arithmetic special divisor and this one cycle. So you can try to use induction to compute this non-constant term. So, and also we need to find a suitable analytic site, means we need to find a suitable Eisenstein series or its derivative to match this arithmetic intersection. And then so we need to construct the so-called arithmetic Ziqi formula to do this match. So actually, in our work, we consider the following, the so-called we call the different series. Here the notation is a little bit complicated. I would like to explain. So the first term, the PR I prime is just here. The PR means the holomorphic projection. So because you take the derivative of the this theta essence series. So here I is a mixed theta essence series because when the phi is split, means for example, this Strauss function can be decomposed into a product of Strauss function. Then this I is just a product of a theta series and an Eisenstein series. So we call this I the mixed theta Eisenstein series. And you take a derivative, but after you take a derivative, it's not holomorphic. So you need to take the holomorphic projection, and everything can be computed explicitly. So the first part is PR I prime is called the derivative series. And for the second part, it looks rather long. So here this mathematical P, again, is the same point defined before. It's just you take the Zariski closure of the same point on the generic fiber. And you also need to normalize at the generic fiber to make it degree 1. And here this Kasai is just this one, also normalized to be degree 1 on the generic fiber. So you take this arithmetic intersection, and then this one is automorphic, as we explained, because this although this part mathematical Z is just taking the Zariski closure, this part may not be modular in the arithmetic sense. But if you take the intersection with any degree 0 one cycle, you then get a real modular form, automorphic form, and this arithmetic intersection number we call this the height series. So this is automorphic. Then we can match these two parts and compute everything explicitly. And then you can imagine we can compute all the non-constant terms and match them, and you can expect some match on the constant term. And as we talk about, the constant term of these different series contains the modular height we need. So after all these explicit computation, you can get the formula of the modular height. So we also like to say our idea of the proof is based on the subsequent works by Yuan Zhang on the Gross-Zagier formula. They generalize the Gross-Zagier formula to the quaternion Shimura curve, and also on Yuan Zhang's work on the average Combs conjecture. And then Yuan used this idea to compute the modular height of quaternion Shimura curve. So all these three papers and our paper, we follow the same idea. So here is a very short example to explain how these three papers, the relation between these three papers. So first, in Yuan Zhang, they prove the formula of Gross-Zagier formula. Essentially, they compute the arithmetic intersection of P and P, just arithmetic intersection between the same points. And then in Yuan Zhang, on their work on average convex conjecture, they prove the height, they prove the formula of height of the same point. And finally, in Yuan, they prove the self-intersection of the Hodge bundle, means the modular height. So from left to the right, you can imagine the Strauss function becomes more and more general. So in Yuan Zhang, you can choose the Strauss function to be very degenerate to cancel many terms. You can imagine these later two terms are cancelled due to the degeneracy of the Strauss function in the first paper. And then they need to consider a more general class of Strauss function because they need to compute the second part. And finally, to compute the modular height, they need to choose the Strauss function to be very standard. For example, it can be the characteristic function of the Hermitian lattice or something like that to be very standard. So this term is not killed, and you can compute this term. So from left to right, you need to compute more and more terms. So this is the main idea of the proof. So I think this is today my talk. So thank you very much.